Buffers, lecture number 25. So now we're going to continue talking about these equilibrium expressions and advance past these equilibriums where we have acids and bases and look a little deeper. And we're actually, at the end of this lecture, going to talk about titrations, the use of these equilibrium expressions in titrations. But what we're going to start with is talking about what the presence, or if we have an equilibrium reaction where we have more than one thing present. Right? And we're going to start by defining what we call the common ion effect. So if we're looking at the effect on a equilibrium expression if we have an ion already present. So the common ion effect is the shift of equilibrium caused by the addition of a compound having an ion in common with a dissolved species. Right? So if we look at, say, the acetate down here at the bottom. So if we add more acetate ion, what does that do to our equilibrium values? Right? From Le Chatelier's principle, it says if we add this, the equilibrium shifts in this way. Right? So if we're adding some of the ion, we're going to cause a shift in the equilibrium because of Le Chatelier's principle back to this completely protonated species. Right? So the presence of this common ion suppresses the ionization of a weak acid or weak base. It's going to cause, Chatelier's principle is going to say that we're going to shift towards this protonated species. Right? Again, if we look at the example that we had here, if we add more of this acetate ion in terms of form of sodium acetate, that's going to cause some of this shift back to the acetic acid. Right? So then let's talk a little bit about this mixture then when we have some of our weak acid, HA, and its conjugate, NA, in this case, this anion A. Right? Our equilibrium position is still dictated by our equilibrium expression. So our Ka is still holding true. Right? But typically in these acid bases, everything we've solved for is the pH. So if we can rearrange this equation so that we look at pH. So we're going to solve for that H plus concentration. So if we do that, we see that the Ka times the HA over A minus is equal to the H plus concentration. Right? We're interested in the pH. So in order to find pH, we take the negative log of that value. So if we have an equation here, we can take the negative log of both sides. Right? From the rule of logs, remember that if the multiplying two things together is the same as adding those when you take the log. So we can take the negative log of the Ka plus the negative log of HA over A minus. Right? If we don't like that negative, we can rearrange or flip it over, so make that a positive. So now we have the negative log of H plus is equal to the negative log of Ka plus the log of the A minus, this conjugate, over H, the concentration of HA. Right? We know that the negative log of H plus concentration, or H3O plus, is pH. Right? We've said before that the negative log of the Ka is the pKa. Right? So now we can simplify this into the pH is equal to the pKa plus the log of the concentration of A minus over HA. Right? So then if we have this presence of both of these species, we can use what we call the Henderson-Hasselbalch equation to calculate the pH if we have the conjugate and an acid. Right? So we take the thing that's acting as the base and put its concentration on top, divided by the concentration on the bottom. And this way, typically, we're only going to talk about initial concentration. So it simplifies our process. And if we have both of these present, if we have the acid and its conjugate or the base and its conjugate, we refer to that as a buffer. So a buffer solution is a solution that contains a weak acid or base and the salt of that weak acid or base, or the weak acid or weak base plus its conjugate. If both of those things are present, then we can have a buffer, but both of them must be present. And the important thing about a buffer, because of Le Chatelier's principle, that we add a stress and we can shift one way or the other, these buffer solutions are going to resist changes in pH upon small additions of an acid or a base. And we can see that from this equations down here. If we add a strong acid to this solution, if it has the acetate ion, that's going to form more acetic acid. If we add base to the acetic solution, which has acetic acid, it's going to form the acetate ion. So because we're just shifting these concentrations back and forth, and once that stress is added, we get a shift back. Right? So these solutions, these buffer solutions, are going to be able to resist pH changes when we add a small amount. Right? How well these, or how much acid or base these are able to absorb before the pH changes substantially, is what's known as the buffer capacity. So the buffer capacity is the measure of the strength of the buffer, its ability to maintain a pH with the addition of an acid or base. So the greater the concentrations that are present in the buffer, both the weak acid or base and its conjugate, the higher those numbers are, the greater its resistance to pH is going to be. As well, the closer those two concentrations are to each other, the greater the buffer capacity is going to be. Right? So because a small change in that is going to be offset by its ability to shift back. So a buffer solution is going to have its greatest capacity when the concentration of the weak acid or weak base is equal to the concentration of its conjugate. Right? That's where the buffer is the strongest, has the biggest capacity to resist change. We can talk further about then the buffer range, how long this is going to last before a small change is going to give us a pretty big change in pH. And that's related to the ratio between the acid and the base. Right? If they're equal, they're at the largest potential, but we see a biggest change over this pH are 10 times the concentrations of the other. So our buffer capacities typically have a pH range of 1 unit. Right? So if it's buffered at a pH of, say, 4, it's going to be able to maintain a fairly stable pH until we get to a pH about 5, and then a small addition is going to cause a large change in pH, or 3. Right? Either way, within that range, we can add quite a bit of acid or base before we get a substantial change. So this buffer range is typically plus or minus 1 pH unit of the pKa of that individual acid component. Right? Where we see these buffer capacities really play out, besides in practical use when we buffer solutions, but where we're going to really see the one practical example of these equilibrium expressions, all that we've talked about for the last couple weeks, is through the use of titrations. So if we remember a titration, it's when we take a solution that has known concentration accurately, and we gradually add it to something that has unknown concentration to allow a chemical reaction between the two to take place. Right? Once that chemical reaction is complete, or stoichiometrically related, we reach what we call the equivalence point. Right? The point where we've added as much of one component that it takes to completely react with this unknown concentration. As you all know from lab, typically the way we follow these titrations is using an indicator. It's a substance that changes color at or near our equivalence point. So if we look here in this figure, we have the titration of a strong acid with a base. So under acidic conditions that we start with, we have a clear solution, and we're going to continue to add base until we've reached this equilibrium or equivalence point, at which point we are going to get this pink solution to occur, right, where we've added as much base as we need to completely react this unknown acid. So if we can follow what these calculations that we've been doing so far is going to allow us to if we know the constant information about the two solutions, we should be able to follow or predict this reaction curve, right? Or these titration curves. And we're going to talk mainly about 3 different types of titrations today. These acid-base titrations. The first one, which is the simplest, is this strong acid, strong base titration. Right? So if we look up here, we have sodium hydroxide with sodium or hydrochloric acid reacting in a 1-to-1 ratio to form water and sodium chloride. If we look at the net ionic equation, we'll see that's going to be OH minus plus H plus goes to H2O. Right? So when this reaction is complete, we're going to add as much H plus or OH as we have the other one present, and that is going to go completely away. So the only thing we will have at the equivalence point is going to be water. So a pH of water at 25 degrees is going to give us a 7. So for these strong acid, strong base titrations only, we are going to get an equivalence point with a pH of 7. Right? But we're able to mathematically predict any point on this curve by looking at what's present. Right? We have a acid and a base, they're strong, so we really have just a bunch of limiting reagent calculations. So our initial pH is going to be determined by the amount of acid that we have present. Right? So if we have whatever unknown concentration we have, that is going to give us our pH. So if we can calculate our pH, we can then predict that concentration. Right? And as we start adding base to this, our pH is going to be dictated by the amount of that H plus that is remaining. Right? So we're going to do a limiting reagent calculation. We figure out how much acid we had to begin with, figure out how much base we've added, subtract those two amounts, and we are going to figure out the amount of H3O plus that we had remaining. It's now been diluted because we've changed the volume, so we're going to have to take into account that dilution, but that's what's going to be determining our pH. At the equivalence point, where we reach the end point, our pH is going to be 7 because it's a strong acid and a strong base. Right? So the only thing we're going to have left there that's determining pH is our water. Beyond the equivalence point, we are going to see that our pH is going to be dictated by the extra OH minus that we've added. So we're going to figure out how many moles of OH minus we've added in excess, account for this dilution, and that's going to give us our pH. Right? So these are the most straightforward, simplest reactions to think about conceptually and do the calculations for, which quite honestly probably means we're not going to do a lot of them, but I want you to be aware of them. They're fairly straightforward. It's just this limiting reagent calculations we've been doing now for about 2 semesters. Right? The ones that are a little bit more interesting, if you want to call it that, would be if we take a weak acid and react it with a strong base. So if we look at here where we're taking the acetic acid and adding sodium hydroxide, right? If we follow this curve here, we see that the equivalence point is no longer going to be at pH 7. It's going to be at some other pH because it's going to be determined by how much of this extra acetate ion, which is also pH affecting, right, that we have left at that equivalence point. So the acetate ion is a weak base, so the equivalence point pH is going to be basic. So for all of these weak acid, strong base titrations, our equivalence points are going to be basic, with a pH of greater than 7. But again, now we have all the information we need to calculate all the values on this titration curve. Right? So if we look at our initial pH, in this case, the example we had here, the acetic acid, the initial pH is going to be determined by the amount of that acetic acid that we had present to begin with. Right? So we would set up an ice table, calculate the amount of H plus or H3O plus that we produce at equilibrium. That is going to be our pH. Before the equivalence point, the pH, what we're going to have is that some of this OH minus is going to react with our acetic acid to form our conjugate. So we're setting up so now we have the acetic acid and its conjugate, that is a buffer. So between the initial pH and the equivalence point, our pH is dictated by Henderson, or we can calculate it using the Henderson-Hasselbalch equation. Because it is a buffer solution. At the equivalence point, now we've converted all of our acetic acid to the acetate ion. So we've converted to the conjugate. So now we have a salt calculation. The same calculations we did before, where we now, instead of an acid, we have a weak base. We set up an ice table, but the only thing we have to consider now is that our concentration has been diluted because we've added all this additional base to it. So we have to calculate our new concentration of this salt, set up an ice table just like before. Beyond the equivalence point, now we have extra base, so our pH is going to be dictated by that excess base added. Right? So it's going to be, we have to figure out how much of that OH minus is in excess, convert that to a concentration, then convert that to a pH. Right? Conversely, we can talk about this other situation where we have a strong acid, weak base titration. Now so for example, hydrochloric acid plus ammonia, right, to give us the ammonium chloride solution. Now we see that we start off with the base, so our pH is going to start high and we're going to end low. Now the NH4 that we produce is going to be a weak acid, so the pH at the equivalence point is going to be less than 7. It's going to be an acidic solution. Right? And we can set up a similar set of calculations there. Before the initial, that's just a weak base calculation. Set up the ice table. This initial part where we're looking at both the base and its conjugate, that is a buffer. So we're going to set up the Henderson-Hasselbalch equation. At the equivalence point, we have converted all of our weak base to a weak acid. So it's one of those salt calculations. And then beyond the equivalence point, our pH is dictated by the excess amount of that strong acid that we've added. So we're just going to be calculating how much strong acid we have in excess and calculating the pH from there. So the calculations for these titrations aren't anything new. We can calculate the equivalence point using stoichiometry, same thing we've been doing now for 2 semesters. Most of the other points we're going to be using ice tables, same thing we've been doing now for a couple weeks. Really what we're trying to follow, and the hardest part about these, is what is determining the pH of this solution. Is it a weak acid? Is it a weak base? Is it a strong acid? Is it a strong base? Do we have a weak acid and its conjugate, a weak base and its conjugate, so we have a buffer? What is it that's really determining what's affecting our pH, and that's going to determine how we calculate these pHs. We're going to finish up here talking about, we said for most of these titrations we estimate the equivalence point by looking at the endpoint via an indicator. Most of these pH indicators are weak acids or weak bases themselves. So what we're doing is, since we're adding a small amount, it's fairly easy for us to change those concentrations by a factor of 10. By changing the concentration of one over the other by this factor of 10, what we're really doing is changing the dominant species, which is going to change the color. So here we have a table of indicators and their colors in 2 different solutions. This is out of a different text. We have one probably very similar in our textbook. But we can see that this transition occurs in one set of conditions. We have one color, and another set of conditions we have another. And that is really determined by a pH value. So we're going to, by estimating where our equivalence point pH is going to be, we then select the best indicator for that. Right? The figure in your book is a little bit fancier, if you will. It gives us the same list with a indication of what color is dominant. So if we look at the top one, that crystal violet, it starts out in very low pHs as a yellow. As it transitions, it goes to a green, and then after it gets past that transition, it's blue. Right? So this crystal violet would be useful for determining pH at a change or endpoints of about a pH 1. Phenolphthalein, which is what we typically use, is when we do a strong acid, strong base, because it's going to give us a fairly It's going to go from colorless to pink at around a pH of 8. Right? If we have a strong acid, strong base, that's going to change at a pH of 7. Gives us a fairly good indicator because it's so dramatic. You've all seen it. It goes from completely colorless to that bright pink very quickly, right around that pH that we're interested in. The one above it, the phenol red, well, closer to that pH 7, is going to go from a yellow to a red, where we want to stop at an orange color. That's very hard to see, right? What it really does is it goes from like a straw yellow, which is kind of hard to see to begin with, and then it becomes orangish red. Right? That's a much harder transition to follow, therefore, compared to the phenolphthalein. So a lot for these pH 7s, we use the phenolphthalein reaction. So what we're always going to do is, depending on what pH range we're looking for, we're going to select the appropriate indicator.